continuous amplitude in string theory. Okay, now there's actually just we're not unless we come across a specific reason, we're not going to do actually any one loop amplitudes with vertex operators, at least at this part of the course. Okay, so the direction we plan to go in now is 2 or 3 fold. So there are 2 or 3 things we want to discuss over the next 2 or 3 lectures. The first thing we want to discuss is to understand in a more structural way the structure of string amplitudes, so as to understand, for instance, how space-time unitarity follows from worldsheet considerations and things like that. Okay, that's one direction in which we want to go. Another direction in which we want to go, which is independent but related, is the following. So far we have been studying string theory. So far we have been studying string theory on in flat space. However, as we've seen, we've developed the rules for string scattering amplitudes in a very structural way. We've got some conformal field theory, which is the theory of 26 free bosons, and we've got the BC coast system, and that having these two inputs allowed us to calculate string scattering amplitudes. Now, the next direction in which we want to go is to generalize this construction. The simple generalization is the following. You see, although we've been working with the free boson theory, actually for most of what we've talked about, not for the explicit calculations, but for the structural program, for most of what we talked about, all that we really needed was to have a conformal field theory with central charge equals 26 on the worldsheet of the string. Actually, it's to be safe, we should say things a little better. You see, in, for instance, proving the no-host theorem, we used the fact that there were 2 directions in space-time that were just flat. You remember the x plus and x minus directions for special x finite. Okay. So, the safe statement, more precisely, is that if you had a sigma on 2 flat directions, one which is time, the other one which is space, times any other central charge c equals 24. Okay? If you think about it, much of what we have, more or less every structural statement we've made about string theory goes through with this replacement. That is, if we all the statements about, say, the no-host theorem, about the spectrum of the theory, about how to construct string scattering amplitudes, go through in an almost automatic fashion if you replace the vertex operators of the flat space string theory with the vertex operators of this arbitrary c equals 24, a conformal field theory, times time and one flat point, time and one space. So the other direction that we want to go in after we study string scattering amplitudes in a little more generality is to look at that generalization. Okay? So although we're going to study this only a couple of lectures from now, I wanted to make a statement now that starts sinking into your consciousness. And that is this. The final rule will be that we can define good string scattering amplitudes for any background that is described by a worldsheet conformal field. Okay? A worldsheet conformal field theory with c equals 24 plus one time one space. That last thing is probably a thing. That last thing can probably be relaxed. But in this course, we will basically focus on this. For large parts of this course, we will focus on these cases. Okay? So, instead of describing, now suddenly we see that string theory, which we started developing as a theory that described scattering in a particular space, suddenly looks like we've got many different string theories. Okay? One for each conformal field theory. There will be a few other restrictions in this conformal field theory, as we will see. The restrictions are automatically met by the free boson theory that we require for this conformal field theory. Modular variants, things. Okay, so any conformal field theory with c equals 26, or perhaps more precisely c equals 24, defines some worldsheet theory that can be used to compute the scattering amplitudes of string theory. So now you might think, wow, what's going on? What we've got now is plethora of different string theories. And in some sense, that's correct. In some sense, it's correct. We've got a plethora of string theories. But there is a way of thinking of this family of string theories that I now want to describe to you, and that we will in a lecture or two understand in more detail. And that is, at least large classes of these different theories can be thought of as different backgrounds for a single string theory. Okay? Now, in order to understand that, what we will do in our course is the following. What we will do is to say, look, the most general conformal field theory is very complicated. But let's try to create conformal field theories that are two-dimensional sigma models on some background in space. The one we've been studying so far is the two-dimensional sigma model on the flat 26-dimensional background. So now let's look at small deformations of this background, but deformations that preserve A, conformality, and B, central charge equals 26. Okay? So we'll see whether we can find small deformations of these conformal field theories that preserve these two properties. Okay? So the kind of thing that we'll do is to write down a sigma model that looks like G mu nu of X, dx, d alpha, X mu, d beta, X mu, G alpha beta. We also introduce an additional term. Epsilon alpha beta b mu nu. Okay, swell G. Okay. So now this is a sigma model, and so the X is run over, let's say, 26 dimensions, so as to easily maintain D equals 26. So this is a sigma model, and it describes some two-dimensional field theory. But this two-dimensional field theory is not in general conformally invariant. Okay? So what we will then do is to work out the beta function for this two-dimensional conformal field theory. Okay, we have a 1 over 4 pi alpha. Yeah. And what we'll do is to work out the beta function for this two-dimensional conformal field theory in a power series expansion in the coupling constant of this two-dimensional field theory. Now, what's the coupling constant of the two-dimensional field theory? You see, the free theory is when these G's are just flat space constant and B is 0. Let's forget about B for a moment. Okay? So suppose you had what prevents G from being transformed with the right coordinates to the flat space metric? Well, it's curvatures. Okay? So curvatures are essentially derivatives of G. So this sigma model, expanded around the free limit, has as coupling constants derivatives of G in units of alpha prime. Okay? So what we'll do is work with the alpha prime expansion of this conformal, of this field theory, and find the condition for this field theory to be conformally invariant with C equals 26. Okay? This is just an advertisement to orient you for when we actually get to it, and so that you've heard the words when we actually get to the calculation. But we're going to find something quite remarkable. What we will find is that the condition for conformal invariance, the condition that the beta function vanishes, okay, is a set of equations on this G and B. And these equations will turn out to be Einstein's equations, plus the equations of motion for a B field in space-time, plus various alpha prime corrections that we can systematically compute by computing the beta function, not the first order in alpha prime, but second order in alpha prime, and so on. We will also find that the equations we get out of this can be reconstructed out of a space-time effective action. And that space-time effective action is the same space-time effective action that reproduces the string scattering amplitudes of string theory. Okay? So, this will give us a way of thinking. This will give us a way of thinking of these other sigma models. instead of thinking of them as being different conformal field theories, which they undoubtedly are, if we think of them from the space-time point of view, what they are simply different solutions. Different solutions to the equations of motion for the space-time effective action of string theory. Do you see what I mean? There is one space-time effective action. We get a conformal field theory when we satisfy the equations of motion of that space-time effective action. Okay? So, a solution to the equations of motion of this theory describes, from the point of view of the worldsheet, a conformal field theory. Okay? So, the different conformal field theories that we get, from the point of view of two dimensions, they're just different field theories. But from the point of view of space-time physics, they should be thought of as different solutions of the same underlying ground. Of course, all this will become clearer as we actually go through the calculations. But is this clear? Is this point clear?
That space-time effective action, will it be valid only for the massless states?
Yes. So the space-time effective action that we'll compute will be the effective action in a derivative expansion. Okay? So it's an effective action in an expansion in alpha prime times derivative. Okay? Now this only makes sense for the massless states, because for massive states the derivatives, at least the time derivative, is a mod alpha, because the energy is mod. So the effective action that we're getting is something that you should think of as integrating out all the massive guys and then working on the effective action for the massless guys in a power series expansion in alpha. Okay? So all of the massive guys are contributing to the answer. For instance,
they're affecting the coefficients.
They're affecting, exactly. You integrate out this massive guy, it gives you this effective 4-point vertex for the massless guys. And we'll see this in two different ways. But firstly, from the string scattering amplitude point of view, it'll be totally clear. You see, because the amplitudes for graviton exchange involve everything from as we've already seen. Okay? So, before we get to a discussion of the general structure of string scattering amplitudes, the thing that we're actually next going to do contentfully. Next, I wanted to say this. I wanted to say that we should think of this discussion as applying only to the free boson theory that we've studied so far. Anything that we say structurally that follows just from the rules of general conformal field theories will apply any conformal field theory in the worldsheet. There are plenty of such conformal field theories, at least a subclass of which can be thought of as small deformations of this flat space background, and at least those guys, can be thought of as different solutions to the one Lagrangian that's describing the physics of the bosonic string. Okay? Now, you see, our understanding of string theory, is, it's not like we have an a priori understanding of the space-time effective action. What we really do have in our hands concretely is the rules for calculating string scattering amplitudes and these beta functions starting from a two-dimensional conformal. Okay? So, some people would word the situation, and so let's review. What I said when we haven't yet seen, but what I told you about is the following: that given any conformal field theory with C equals 24 plus 2 flat space, okay, that satisfies a few other additional constraints, we can define well-defined string scattering amplitudes with this conformal field theory. You get a spectrum that obeys unitarity and blah blah blah, all the good properties you want. Moreover, at least classes of these can be thought of as being, solutions of the effective action of string theory that you can construct in some other way, namely from reproduced from the string scattering amplitudes. So, some people, me included, would take this situation and word it as follows. We'd word it in the following way. We'd say that in string theory, while we don't really know what the space-time effective action is, except in certain limits, for instance, the alpha prime expansion, we in computing and so on. However, what we do know is what the set of solutions of the space-time vector is. And the set of solutions is given by all two-dimensional conformal field theories. Okay? That obey certain properties. Okay? Let me say this again. Classically, the set of classical solutions of string theory, okay, can plausibly be identified with the set of classical solutions of string theory can be plausibly be identified with the set of all C equals 26 conformal field theories that obey a few additional restrictions. Okay, that is that is actually, if you think about it, a very beautiful statement. You see, we don't know solutions to what, but this is the solution space of the theory. Okay, so except in certain limits, we don't understand string theory off shell. Field theory, we can write out an action, and we can separate the question of whether we understand the action from the question of whether we understand the solutions that follow from there. Except in certain limits, today we don't have a fully satisfactory understanding of string theory off shell. We don't know what string theory action is, except in certain limits. However, much beyond these limits, we do think that we have a very plausible guess to the question of what all the solutions to this action. And the answer to what the solutions to this action are given by some functions in space-time. It's given by much more abstract construct. The space of conformal field theories in two dimensions. You see, now because some conformal field theories can be thought of as sigma models of some target space. It's possible to look at conformal field theories with such minimal models in two dimensions. Things we'll study as we go on in our course that have no plausible interpretation in terms of sigma models in target space. Okay? So the answer to the question of what the set of classical solutions of string theory is, as we will develop in this course, will turn out to be a much more abstract and much more interesting answer than saying by some functions in space-time. It's this answer. It's the set of conformal field theories of the theory. And now this answer goes beyond the question of keeping track of only massless degrees of freedom. You see, we could be dealing with conformal field theories that if you thought in terms of sigma model language, would be curved and string scale, where all the massive degrees of freedom of string theory are as important as massless degrees. Okay, now this statement that I've made, we will sophisticate as we go through the course. You see, I keep emphasizing this statement gives us the set of classical solutions of string theory. But as we go through this course, we will learn that whether the solution is classical or not sometimes depends on your point of view. We will study string dualities, which will trade situations in which something is very classical to something which is very quantum. So we will see that this is the tip of an iceberg in a much larger solution space of this theory that we have encountered. But for a first encounter, this is not a bad statement, and it already introduces you to the power of abstract thought in some way. It's this beautiful statement that the set of classical solutions to string theory are the conformal field theories in sequence 26 and certain other constraints. Okay, any questions or comments about this general philosophy before we proceed?
Okay.
Please.
I just wondered about this string theory. We do not know what string theory is optional.
Yeah.
If we are doing loop level computations, how is it so that when we are doing loop level computations, aren't we considering it to be optional?
No, you see, what we know is the rules for how to calculate scattering amplitudes on shell. You see, including loops, but on shell. For instance, we don't know how to, we've seen this in many different ways. The first way in which we've seen it is that whether classically or at loop level, we don't know how to calculate correlation functions in string theory. We only know how to calculate scattering amplitudes. By which I mean,
But we have intermediate states where there are, when we are doing loop level computations, we have string states which are in the loop.
Yes.
And so we are even those loop states we are considering them to be
on shell. No, those loop string states do whatever they want. So in some sense, it's a good point. So your point is that, well, suppose we take external particles on shell, the internal particles run overall momentum, and in some sense that's true. So maybe it is possible, to. Well, no, that's probably not. Okay, so you might have the following conjecture. You see, by on shell, what I mean is that we know the only things that we can calculate are putting external particles on shell. Okay? There's no clearly defined sense in which you can calculate correlation functions of operators that are inserted in a manner that doesn't obey that equation motion. You can't compute insertions of A of P at any B. You can only do it with P squared is equal to M squared, as we've seen, right? Because it's only then that we get 1, 1 vertex operators. And the rules of string theory make sense. Everything else is gauge related. Now, you might say that, however, by effective cutting, should be enough information in principle to determine what the correlation functions are. Maybe not. I'm not sure if that's true. But okay, this is a statement. The statement is that we can compute only on shell external leg insertions, but to arbitrary length. It could well be that. The other point is that we can only do this in perturbation theory. That order by order in a power series and expansion coupling constant. Let me give you an example. This is more a question of perturbation theory than on shell versus off shell. But let me give you an example of two theories that are different off shell, that would have identical perturbative expansions in quantum field theory. Okay? These theories are QCD with different values of the theta parameter. Okay? Because the theta parameter multiplies a total derivative, it just doesn't affect Feynman rules at all. So all of the Feynman rules of QCD with different values of the theta parameter are identical. Nonetheless, the theories are different. The instant-on contributions are different in the two theories. So it's certainly not generally true that the perturbative expansion determines the theory. Your question is, of course, a little different. Do on-shell expansions. Okay, we have two restrictions. We only have perturbation theory at the moment, okay, and we only have on-shell. That's probably not enough to determine Lagrangian by itself. Okay, I shouldn't say too much more. This is the situation as I understand it. Okay, that's a good question. Should be thought through. It seems to me to be likely that there is some philosophical sense in which off-shell string theory is not a very good thing to consider, basically because of geomorphic invariance, as we've discussed before when we discussed scattering invariance. Because the question of calculating Green's functions linked to where these Green's functions are calculated, which is not simply gauge invariant under diffeomorphisms, as we've discussed before. But all such philosophy should be taken with many pinches. Okay, good. Other questions or comments about this? Okay, so now let's turn to the more mundane job of actually, this is a very interesting job, of actually trying to understand the general properties of string animals. Okay, and we're going to first try to understand general properties of tree-level string amplitudes in a slightly abstract setting. In order to do that, we're going to back up and try to understand some properties of conformal field theory. We're going to try to understand some properties of conformal field theory in the sphere that we could have discussed long ago when we were first discussing conformal field theory, but I thought I would postpone the discussion of that to nearer to where we would actually use these things. And the properties of this conformal field theory and sphere that we're going to discuss has to do with the Hilbert space interpretation, more about the Hilbert space interpretation of the path integral with insertions. Okay, so but before we even get there, let me quickly review a few consequences on four correlation functions that follow from conformal invariance of the sphere. Okay, so the first thing we're going to talk about is what are the set of globally well-defined conformal transformations on the sphere. Okay, so we're asking a technical question which will soon have interesting consequences for us when we study correlation functions and blah blah blah. But let's first focus on this technical question. What are the set of globally well-defined conformal transformations of the sphere? Okay, now infinitesimally we have already answered this question. Can somebody remind me what the answer to this question is infinitesimally? How many different conformal transformations? Infinitesimal. What's another name for an infinitesimal conformal transformation? What's the name for an infinitesimal diffeomorphism that doesn't change the metric? What parameterizes such diffeomorphisms? Killing vectors. What's the name for an infinitesimal conformal diffeomorphism? Conformal killing vectors. Very good. We've studied the conformal killing vectors in the sphere. What are they? Come on. How many are they? Good. How many? First thing, they're holomorphic functions, right? They're zero modes of C. Okay? They're holomorphic functions. Which holomorphic functions? How many? 3. 1 z and z squared. Okay? So infinitesimally, suppose we wanted to redefine a coordinate z as a function of some parameter t. Okay? The change in z with respect to t is infinitesimally given by a plus bz of t plus 3z cz squared. Now, if we want to understand what the global structure of these well-defined conformal diffeomorphisms of the sphere is, okay, what we do is take this equation and integrate it. Okay, the first thing, though, for two of them actually, so let's see. We'll put together the answer. We could actually do this integral directly, but we'll put together the answer a little more cleverly. What about this? What is the global version of this guy? I mean, it's obvious to do the integral in your head. Yeah, so it's z of t is equal to z of 0, which is the original guy, okay, plus a times t. T is arbitrary, so some constant, versus this translation. Right? Suppose only b was non-zero, what will you get? Exactly, and t is arbitrary, so it's a constant scale. Okay, from b we would get z is equal to z of t is equal to z and e power bt. Okay, so this is z is equal to lambda and z. These two we knew. These were the obvious conformal diffeomorphisms in the theory. Translations clearly are diffeomorphisms. I mean, clearly the metric conformally unchanged, and scaling clearly leaves the metric conformally unchanged. But the new and interesting thing here is this guy. So let's try to understand what happens with this guy. Exactly. So dz by z squared is equal to dt times c. Okay? So we get 1 over z of t. Okay, actually it's the other way around. Minus 1 over z of t plus 1 over z is equal to some constant. That's all that constant C equal to is. It's a different C, that's all it is. It's arbitrary. Could be. Okay, so let's solve now for Z of t. So we get Z of t is equal to 1 over 1 by Z minus d. Okay, so Z of t is equal, which you can think of as Z prime, is equal to Z over 1 minus dz. Okay, so that's what we get by integrating this conformal transformation. Now, we don't need to do these things one at a time. We could do them, we could first make this coordinate change, and then do a scaling, or then do a shift. Okay, if we do a scaling, what do we get? We get, we change this by a factor of a. If we do a shift, what do we get? We put some constant here as well as here. Okay? So, by playing through all of these operations together in your head, okay, you can convince yourself that the most general such change of coordinates can be written in the following form. Z prime is equal to AZ plus B over CZ plus D. Now that looks like it has 4 parameters. Whereas infinitesimal we have 3 parameters. But the 4 is a fake. Because if we take A goes to A times lambda, all of them. B goes to B times lambda, C goes to C times lambda, D goes to D times lambda, you haven't changed Z prime. Okay? So this coordinate transformation is defined by A, B, C, D up to this overall scaling. And it's conventional. It's conventional to fix this ambiguity of overall scaling by choosing AD minus BC equals 1. Maybe choose lambda so that that's true. Okay? So if you think of this as a matrix A, B, C, D, the determinant of this matrix is 1. Okay? So that tells us. Okay. Now, this is an exercise that I proposed to you for measuring the changes in modular parameters, but it's exactly the same algebra. You can convince yourself that if you perform one of these transformations and then another one, of course you get back to one of these transformations itself, but that the matrix of parameters, the effective matrix of parameters that you get for this combined transformation is simply the product of the two matrices of the original transformation parameters. Okay? So this class of globally well-defined conformal diffeomorphisms of the sphere is simply the matrix group SL2Z. Not Z, SL2C. SL2C. Is this clear? The parameterized by matrices which are determined equal to 1. Okay, and you multiply elements in order to compound these things. Okay? So the class of well-defined global diffeomorphisms on the sphere is this group. It's sometimes called the group of Mobius transformations. Okay? It's coordinate definitions by these SL2C matrices, and they follow the rules of matrix multiplication of SL2C. Okay, good. Questions or comments about this? Fine. Now, because these conformal diffeomorphisms are well defined on the sphere, globally well defined on the sphere, they imply certain properties. The fact that you have this well-defined global symmetric group on the sphere implies certain properties of correlation functions of conformal field theories on the sphere. Okay? And it's these properties that we're now going to try to uncover. The material I'm discussing now, by the way, is the end of chapter 6, and after that we'll jump to the beginning of chapter 9. Okay, so to simplify the discussion, for some of it it's not completely needed, but to simplify the discussion, let us consider operators A that are what Bulchinski calls tensor operators. And by tensor operators, he means that they transform, if not under the whole conformal group, at least under this SL2C subgroup of the conformal group, like they are primary operators. Okay? So let's write that down in the equation. You remember our primary operator conformal field theory transform. You have A tilde of f of z times df dz to the power h times df bar dz bar to the power h bar was equal to A of z. Okay? So suppose you've got an operator A in the coordinate z, then you perform a conformal transformation such that this z is f of z prime. Okay, so that the insertion at z is now the insertion in the new coordinate at f of its new coordinate z prime. You might want to call this z prime. Fine. Okay. Okay. Then the insertion A tilde you have to put in the new coordinates in order to get the same values of correlation functions as the insertion A in the old coordinates. Okay, is related to A by this formula. Is this clear? Okay, under the conformal transformation, z is equal to f of z prime. Okay? Fine. So we are going to look at those operators for which this relationship is true, if not for all f's, at least for those f's that are SL2C transformations that are well defined in the sphere. Okay, and we're going to use this to study consequences of correlation functions. Okay, so let's start. The simplest question we're going to ask is the following. Okay, what is the 1-point function of A00? What can we say about the 1-point function of A00? Okay, so in order to do that, let's choose f of z to be equal to lambda z. Okay, so what do we get? We get that a tilde of 0, 0 times del f by del z, so that's lambda to the h, lambda bar to the bar h bar, is equal to A. But now what is this quantity? This quantity is simply the same calculation in the z prime variables as this quantity. You know, A tilde is the same operator as A was in the new variables. Okay, so this quantity is just equal to this quantity. Do you understand that? Okay, therefore we get the conclusion that A of 0, 0 is equal to 0 unless by taking these two to the same side and subtracting and blah blah blah. Okay, so either A0 or 1 minus lambda to the power h times lambda bar h bar is 0. Okay, which is only 0 if h and h bar both 0. Okay, so we conclude that the only operator that has a non-zero 1-point function, okay, that can have a non-zero 1-point function. Only operators with both h and h bar equal 0 can have non-zero 1-point functions in conformal field theory. We will often be interested in conformal field theories that are unitary, and we've already seen that the only such operators the identity operator. So basically, apart from the identity operator, there's no other operator than non-zero one-point function. Of definite weight, no other operator of definite weight can have non-zero one-point function in formal fields. Okay? Great. The next thing we want to do now is to study the two-point functions and operators. Okay? So, let's do the following. Let's study A of z bar with B of 0, 0. Let's study this two-point function. Once again, let's first apply this conformal transformation. Apply the conformal transformation in question. Let's apply the conformal transformation in question with the simple function f of z is equal to lambda z. Okay? So, what do we get? Well, if we did this here, what we get is del f by that. So that's lambda to the power. Okay, and suppose this guy has weight h1, this guy has weight h2. Okay, then we get lambda to the power h1 plus h2, lambda bar to the power h1 bar plus h2 bar, times whatever this function is. Let's call whatever this function is. So this thing is some green function. Let's call it some g of z z. Now once we do this change of variables, what we've got is the same function computed in the new coordinates, but at points lambda z and lambda z. So this is times g of lambda z bar is equal to g of z z. Is this clear? Okay? How can this equation be satisfied? Well, it can only be satisfied if g of z was powerless and with appropriate powers. So we conclude from this that g of z is equal to 1 over z to the power h1 plus h2, 1 over z bar to the power h1 plus h2. Is this clear? Okay. Now let's study two-point functions in a little more detail. So far we've concluded that this g must have this basically positive dimensional analysis. It's basically scaling both sides correctly. But now we get something that's a little more interesting out of this. And in order to do that, what we're going to do is now look at conformal transformations that are not just translations of shifts, but of an arbitrary eccentric Z transformation. Okay, so let's do the same calculus. So now we know that G is of this form. Okay, but let's see if we get any more information about what about the structure of G from doing from that equality using an arbitrary eccentric Z transformation. Okay, so suppose we write an arbitrary eccentric Z transformation f of z is equal to az plus b over cz plus d. Now let's compute del f by del z, because we need that for this rule. So del f by del z is what? Well, we get two terms. We first differentiate the numerator, then differentiate the denominator. So the first term is a over cz plus d. Okay, and then you get minus c over cz plus d the whole thing squared. Okay, which you can simplify to AD minus BC over CZ plus D.
That is it plus B minus C.
What?
The second term is an is it plus B in the numerator.
The second type. Right, exactly. Thank you. because of this term you get what I said. If you take the CZ plus D on this side, you get the ACZ term cancels. So it's only constants that's left. And the constants that are available are AD minus C. Okay? But if you decided to use convention such that AD minus BC is equal to 1, then this thing is equal to 1 over CZ plus D, the whole thing. Okay? So, what do we conclude? We conclude that it must be that 1 by CZ plus D to the 2H plus H bar. This is del F by del Z. Okay. 1 by CZ plus D to the power 2H plus 2H bar times 1 over AZ plus B over CZ plus D to the power H1 plus H2 times complex conjugate, which I won't write down, right? Is equal to 1 over Z to the power H1, Z bar to the power H2. Is this clear? We're writing down the rules for transformation and the fact that though it's in the new variables of a new theory, a correlation function is a correlation function. This is a function of the new Z. Right? You get the same answer. Is this clear? Okay, okay, fine. So now let's work out the algebra. So what do we get? That works, right? I'm sorry, I didn't wrote this wrong. This should be at the two different points, right? Yeah. Okay, let me write this as Z1 and Z2 instead of Z and 0. Sorry, let me write this again. Let me write this again. It should be how does it go? 1 over CZ1 plus D to the power H1 2H1 1 over CZ2 plus D to the power 2H2 times 1 over, and now we should have Z1 2 to the power H1 minus H2. So let's write that down. So Z1 is AZ1 plus B over CZ1 plus D minus AZ2 plus B over CZ2 plus D to the power H1 plus H2. And I'm not going to write the anti-identity stuff. That this is equal to 1 over Z1 minus Z2 to the power H1 plus H2. This is what must work. Okay, now let's simplify this guy. Okay. You see that the terms that involve Z1 times Z2 cancel because they come with an AC here and an AC. The terms that involve just a constant also cancel because they come with a BD here and a BD here. Okay? So the only terms that are non-zero are those that involve just a Z1 or just a Z2. Let's look at the terms that involve just a Z1. From here we get AD and from here we get BC with the minus sign. So that's 1. Similarly, what about Z2? From here we get BC, from here we get AB, but with the minus sign, so that's minus 1. Okay? So, the left hand side here The left hand side is 1 over CZ1 plus D into 2H1, 1 over CZ2 plus D into 2H2 times what? Times CZ1 plus D into CZ2 plus D, the whole thing to the power H1 plus H2, and then divided by Z12 to the power H1 plus H2. This must be equal to 1 over Z12 to the power H1 plus H2. So these two things cancel. So if this equality is to hold, this term must be equal to 1. Well, but what is it? What it is 1 over CZ1 plus D to the power H1 minus H2 into 1 over CZ2 plus D into H2 minus H1. This thing is equal to 1 only if H1 is equal to H2. If and only if H1 is equal to H2. Okay? So satisfied if H1 is equal to H2. Is this clear? Okay? So while scale invariance, while translational invariance told us that any correlation function is only a 2-point function, it's a function of difference between coordinates. And scale invariance told us that the answer must be a power law equal to H1 plus H2. Full Mobius invariance tells us more. It tells us that it's impossible to have a non-zero 2-point function between operators of different scale equivalents. Okay? This is not something you just sort of weight counting, but it comes from full conformal invariance. Okay? Great. Now let's turn our attention to 3-point functions. Okay, so as I'm going to leave several things as exercises for you guys, but let me at least take the results. Okay, suppose we have a 3-point function between an operator A of Z1, B of Z2, C of Z3, and the weights of these operators are H1, H2, H3, and similarly for the anti-analytic behavior. Okay. Question: what can we say about the Z1, Z2, Z3 dependence? What can we say about the Z1, Z2, Z3 dependence of this 3-point function? Now, first I want to convince you that Z1, Z2, Z3, that dependence of the 3-point function must be completely determined just by conformal dependence. Why is that? Can somebody give me an answer? Can somebody give me a reason? Exactly. You see, we've got a 3-parameter conformal group in our hands. Using this conformal group, we can fix the positions of 3 points. So we can fix the positions of the 3 points to be, for instance, 1, 0, infinity, or any 3 points we want. Okay? And then using the Mobius transformations of these objects, we can then determine what the correlation functions are, an arbitrary function of Z, in terms of these 3 points. Okay? Now, the actual determination I'm going to leave for you guys as an exercise, which I strongly suggest. It's the same kind of technique that we've been using. You employ the constraints of well, what can you say immediately? You can say immediately that it can only depend on differences between Z1, Z2, Z2, Z3, Z3, Z1. That's from translation dependence. Okay? You can say immediately that the dependence must be power law in these differences, and that the sum of powers must add up to the sum of weights. Okay, that will follow immediately from scale invariance. Okay, but the more interesting actual dependence will use Mobius invariance. Okay, and I want you to check, and let's try to get them. H1 plus H2 plus H3. Yeah. Now the dependence of Z1, Z2, Z3 is necessarily fixed to be of this. Okay, times some overall constant, which of course math determines. Okay, now suppose you were doing 4-point functions. If you're doing 4-point functions, how many variables is the answer completely determined by conformal dependence? No. But how many variables does the answer actually depend on? 1. Because you can fix 3 points, but the 4th point is free. So there's a sort of conformally, there's a sort of invariant way to state this. The cross ratio Z1 to Z3, 4 divided by Z1, 3, Z3. Well, it's not immediately obvious. You can check with a little bit of algebra. Now this thing is actually Mobius invariant. That you perform the Mobius transformation of Z1, Z2, Z3, and Z4. Check how this thing transforms under the Mobius transformation. This thing is actually Mobius invariant. So a 4-point function, while it cannot depend randomly on the positions of insertions of all operators, can depend in an arbitrary way on this cross ratio. Okay, and then there are similar more complicated statements you can think about higher functions. Okay, good. So that's all I'm going to say about correlation functions and their structure as is determined from Mobius invariance. Let's summarize. 1-point functions are always 0 except for operators of weight 0, 0. 2-point functions are power law with the obvious weight. The only surprising statement is that, or the only non-obvious statement is that 2-point functions can only be non-zero between operators of equal weight. 3-point functions, there's no restriction. All kinds of operators can have 3-point functions. However, the position dependence of the 3-point correlation function is completely determined. 4-point functions and higher have undetermined functions in them, functions of invariant cross ratios. Okay? Questions or comments about this book? Okay? So this is true for correlation functions of operators in the conformality theory on the sphere. We've crucially used Mobius invariance to explain this. Mobius invariance applies to conformality theories on the sphere. Okay, great. Fine. So now that we've got this out of the way, now that we've got this out of the way, the next thing I want to do is to give you a Hilbert space interpretation. A Hilbert space interpretation of correlation functions on the sphere. Okay. So the thing that we want to try and interpret is the following. Okay, so suppose we do the following. Suppose we've got E prime, and I'll tell you what this means. On the sphere. Now what is A prime? Okay, by A prime I mean the A operator in the U equals 1 by Z coordinates. Okay? So let's say what that means more precisely. Okay, remember that A prime times du by dz to the power h. And a similar thing for anti-analytic, which I'm just not writing but is always there, okay, is equal to a. So a prime is equal to z, u is 1 by z, so it's 1 by z squared minus z squared to the power h times a. A is everything. So, had I been really correct, I would have written it as a prime 0, 0. Because the u coordinates were at 0, 0. But you know what I mean, right? A prime is inserted as unit. It's this mixed notation. It's a notation, unfortunately, that Polchinski uses. It's right, a prime 0, 0, which is a infinity infinity. But not quite a infinity infinity. It's z minus z squared to the power h times a infinity. Okay? Now, let's first see that this, before trying to interpret it, let's first see that this thing is well defined. You might worry that this thing should just be 0 because it involves inserting one operator at 0, the other operator at infinity, and we saw that the 2-point functions are 1 over z to some power, some positive power. If you put z equals infinity, you get infinity. I mean, you get 0. Okay? But that is precisely compensated for by this part. See, so this 2-point function is what? It's minus z squared. So let's try this. Minus 1 to the power h times z to the power 2h times a infinity b 0, 0. Now what is that? Now this is just simple correlation function. Okay, so let's think of this in a regulated fashion. Let's think of this as z bar and the limit z goes to infinity. Okay, what is this? This is now the usual correlation functions. The correlation functions, 2-point functions, rules we've just deduced. So this thing is 0 unless a has the same weight as b. And when it's non-zero, this thing behaves like 1 over z to the power 2h. So the z 2h cancels. Okay, we get some number. Okay? So firstly, this quantity is well defined. Now let's try to understand what this quantity is. In order to understand that, let's take the sphere of the complex plane and divide it into two regions. There's the region mod z less than 1. And there's the region mod u less than 1. Okay. Now, we know what the path integral with an a insertion in the mod z less than 1 disk gives us on the boundary of that disk. It gives us the wave function corresponding to that operator. Okay? So this thing gives us psi of whatever the fields in the theory, let's call them x, of sigma. Okay? For the state corresponding to the operator A. Similarly, what we get from the other side is chi of x of, and this time it's 2 pi minus sigma, because the sigma for 1 by z and the sigma for z go the opposite direction. Okay? So, we've done most of the path integral that computes this 2-point function. We've done the path integral everywhere except on the line mod z equals 1. Yeah. Raju, where is this talk today? 80 at what time is it?
4 o'clock.
Okay, yeah. Good. I'm going to have to wait for this 4 o'clock. Okay, yeah. So let's get as fast as we can. So we get psi of x of sigma times chi of, let's call it psi of sigma times chi of 2 pi minus sigma. And then this thing integrated over dx. Okay? So what is this object? You see, this object is some sort of number that you get by pairing the two. Some sort of number that you get by pairing two wave functions. Okay? And you might be tempted to first guess, well, this thing here should be thought of as an inner product, you might be tempted to think. Okay? This thing should be thought of as an inner product between the two states. But it can't quite be an inner product. Can somebody tell me why? Can't quite be different. Can't quite be the usual quantum mechanical inner product. Why? Exactly. This is a bilinear operation. That should be linear and linear. An inner product always a complex operation. Okay. Nonetheless, then this is a useful pairing of wave functions. Okay? It's a useful pairing of wave functions. It was first, its importance was first or equal to the pairing of operators. Okay? And its importance was first realized by Zamonovikov. And this thing goes by the name of this. It's a bilinear form, non-degenerate bilinear form on space of wave functions. You can also think of it as numbers as relating to operators. And this quantity, O prime infinity I, infinity O J, is sometimes called the Zamonovikov metric, Gij, on the space of local operators, that's going to be space of wave functions of the same. Okay, so the definition. This quantity is some pairing of wave functions or equivalently local operators in this theory, and is written as metric. If we, for a moment, deal only with bosonic operators, you can easily convince yourself that this thing is symmetric between I and J. Basically, by changing from variables Z to variables U. Then this guy gets inserted at 0, 0. This guy gets inserted at infinity, infinity. Since it's bosonic, you can interchange the orders without trouble, so it's the same thing. Okay, so it's a symmetric pairing of operators. It would be anti-symmetric if it was fermionic, because the last step would be without minus sign. Okay, so it's a symmetric pairing of operators or states in this theory, and this is called the Zamonovikov metric. Okay. The Zamonovikov metric is also, as is apparent from our construction here, the 2-point function of the two operators if they're separated by unit distance 1. Can you see that? See, because this quantity here, suppose AB had 2-point function alpha times z divided by z to the power 2h, then this thing would have retained the alpha. Okay, so if you just did z equals 1, you would get alpha. Okay, so more invariantly, you can write down the 2-point function of a OI and OJ. Z1, OJ, Z2 is equal to Gij divided by Z1, 2 to the power 2h1, which is the same thing as Z1, 2 to the power 2h2, because this thing is non-zero only when h1 is equal to h2. Okay, so far we've described this. You could treat as an alternative definition of the Zamonovikov metric on the space of operators and wave functions. But now, the next thing we want to study, okay, we will often find it useful to regard this object as a metric on the space of all operators of wave function, and in particular, we'll define its inverse as an inverse metric, and we'll use it to lower and raise symbols freely. Okay. Now, the next thing we want to study, is what's the connection? Or maybe I should talk about 3-point functions. Okay, let's first generalize this discussion to 3-point functions. So let's do this guy. OI prime infinity infinity, OJ of 1 1, and OK of 0 0. Let's call this notation I KJ squared. let's see what we can say about this object. Okay, in order to try to compute this object, what we're going to use is the operator product expansion. Okay, this we take the OP between these two guys, being thought of as being nearer to each other. They're clearly nearer to each other than to any other operator insertion. That's here. Okay, so as we've seen in our general discussion of the formal field theory, this guy can be written as C M Kj over that is OM over Z to the power some power, but Z is just 1 in this case, we don't need to know power. Okay, summed over everything. Okay, now plugging that into here and using our definition of the 2 point of this 2 point function being the metric, we get GIM CMKJ summed over all M. But we decided that we're going to raise and lower symbols in this theory with this 2 point function, with this metric. So this we can just simply write as CMJ. Okay, this we can simply write as CMJ. Okay, now exactly as in our discussion for 2 point functions, you can regard these CMJs as characterization of 3 point functions. Sorry? CI. Thank you. In particular, you can exactly the same way as we did for 2 point functions, convince yourself that OI of Z1, OJ of Z2, I think I wrote this K, OJ of Z3 is equal toCijk times that cross ratio thing that we had. Z1 2 to the power H1 plus H2 minus H3 blah. Okay, these are completely equivalent definitions and okay, now I'm sorry if we're going through all this formal stuff. But we will find it very useful in our general analysis of string algorithms. Okay, so today's lecture is largely formal, but we'll put it to good physical use next lecture. So don't worry. Okay, so now perhaps the last. We could go on to discuss 4.0. We'll do that when we need it. Perhaps the last conceptual point I want to discuss here is the relationship between this pairing of wave functions. Okay, between this pairing of wave functions, the pairing of operators, and the usual inner product on Hilbert space of this pairing. Okay. The result that I will show you is that if we denote, okay, now Gij, Polchinski denotes as Ij. He puts this double line here to tell you that it's not the usual quantum mechanical inner product. This double line. It's this pairing between wave functions arithmetic. Okay? On the other hand, the usual inner product is denoted by Ij. The question we're going to try to ask is what is the relationship, if any, between these? Now, the key difference between this pair and the actual inner product was the absence of a complex conjugation. Okay? So, roughly what we want to say is that the pairing between a complex conjugated I state and a J state is the inner product between I and J. Okay? That's the statement I want to make precise. So, I am going to the thing I'm going to try to explain to you is that Ij, the usual inner product, is equal to O dagger I infinity Oj 0 0, where under a suitable definition of this, of the Hermitian conjugate, under a suitable definition of this Jaeger operator acting on a Y. Okay, this is the last formal thing that we need to understand before we proceed to our studies tonight. Okay, so let's try to understand this. In order to understand this, I first have to give you the definition of this OI diagram. Okay, so what I want to do is on Hilbert's space. What I want to do is on Hilbert's space simply complex conjugate the wave function. Okay, but we have to ask, how does this complex conjugation, which is something that you do in Euclidean, in Minkowskian space, and in the W picture, because that's where Hilbert space is well defined, on the cylinders. Okay? How does it translate to the Z picture, and how does it translate to Euclidean space? Okay? So, to start with, I'm going to ask a simpler question. I'm going to ask the following classical question. Suppose we've got a certain classical function of weight h, a certain classical function of weight h and h bar, and it's expanded in w coordinates. Suppose I've got a certain classical function O, which is expanded in w coordinates, like e to the power I n w, where now I'll have a nightmare keeping track of conventions, but that's n, where w is equal to sigma plus I tau. Okay, I'm going to have a tough time keeping track of a particular sign, but we'll try to get that. Okay. Now let's remember what the definition of our Z coordinate. Maybe we should stick to Cauchy. Maybe we should stick to Cauchy. Well, there was an extra line right from Cauchy.
E to the power minus I w.
To the power minus I w. So that's
time should increase radially.
Yes. So you're saying Z is equal to e to the power minus I w. Let's check that. Good. So time increases radially, and we go down to anti. Okay, let's use these. This may not be exactly what Kuczynski uses. This is good enough for us. Okay, let's use this. Okay, so Z is equal to minus I w.
Right, because it's 1 over z to the power.
Exactly. Okay, so now right. And actually, let me even back up one step further. You see, what I've done here is to be Euclidean on both sides. Okay, let me even back up one step further and start with the Minkowski theory in W. Okay, so then we will knock out an I. And there may be a plus minus sign here we have to be careful about, but let's worry about what that sign is. Okay, so let's start with this step. Okay. Yeah. Now the key point is, can somebody remember should creation operators go like which operators when you expand the harmonic oscillation? Which ones go like e to the power it and which ones go like e to the power minus it? So let's see. So the wave function associated with the state is 0x times psi. So the thing that should have positive energy is the annihilation operator. operator, because that gives you positive energy.
Yes, sorry.
And positive energy is e to the power minus t. Right. So the annihilation operator should have e to the power minus I omega. And so and in our business, annihilation is positive n. So we probably want to start with this. Yeah, this would be the usual expansion. This would be the usual expansion of right, because the positive n, O ends with positive n. For instance, del x here, which was positive n. Okay, will have which are annihilation operators will have positive energy. Okay, so this is our starting point. Omega is equal to sigma minus tau. Omega is equal to sigma minus tau. So we've got e to the power I n omega times omega. Okay, this is the expansion of an operator or classical field. It's at the moment it's just the expansion of a classical field, but with this convention, with this way of setting things out, the guys with positive n will be interpreted as annihilation operators, and negative n will be interpreted as creation operators. Okay, good. So now suppose I just have this classical field, or actually a quantum operator expression, and I wanted a complex conjugate it, what would I get? If I wanted a complex conjugate, what would I get? Well, I would get that O star is equal to sum over e to the power minus I n omega, okay, times O n star. Okay, sum over n. Very good. So these are the two operators that in Minkowski space are complex conjugates of each other. Or the two functions that in Minkowski space are complex conjugates of each other. Now the next thing we do is Euclidean continuation. Okay? So the Euclidean continuation is tau goes to I times tau. Now we're getting that sign right. That sign can sometimes be important. Let's check for a potential term in a Lagrangian that appears with the dt there's an ion reaction and it comes with a minus sign. This thing should contribute with a minus sign after analytic continuation, and so t should go to minus I t. Okay, so we go to minus I is going to. Okay? Okay, good. Good. So once we've done this, now we define. Okay, right. Now we define. Okay, we shouldn't even have called this down. Let's call this something else. Let's call this sigma minus 3. There's no need for name. Now we define W, which is sigma minus and then tau under this replacement plus I times tau. This thing is now what we want. Okay, so under complex conjugation, what have we got? Yeah. Under complex conjugation, we've got that O goes after analytic continuation. O is now sum over n e to the power I n w O n, but O star is equal to sum over n e to the power minus I n w No, not W star. You see, here this was correct. And then we just take these two analytically continued. What we're looking at is the analytic continuation
of O star.
of O star. Okay, O star was this. This is
Sigma minus.
it was this. When we analytically continue, then we get this. Okay? So the analytic continuation of O and O star are both written in terms of W. Okay? Now what we have to do is to rewrite this as the expansion. Now what we have to do is to rewrite this as the expansion of these operators in the semi-coordinates. Okay? Now that picks up, apart from additional factors of I. Okay, we should. Okay, I really have to go this up. Let me give you two. I'll complete this in more detail next time. Let me just give you the punchline. Okay. See. Now we translate this to Z coordinates. What we get then is additional fact. So this translates to On by Z to the power n. On by Z to the power n. But then we'll also get a plus h from the operator change. This del f by del z that we've been discussing. Okay? And there'll be some factors of I which we'll keep track of carefully next time. Whereas this guy will go to On star over Z to the power minus n plus h. You know, it's just the same thing. On and On star the same way. Okay. Now, so the complex conjugates, we complete this next time, but the complex conjugate of the operator O is effectively obtained, okay, by starring these coefficients here, okay, and then doing some funny things to these z's. Okay, we have to do this more. Let me complete this properly next time. Okay, so this is the natural. Anyway, this is going to be the notion of complex conjugation that we will apply to operators in the Z space. It's the natural notion of complex conjugation because this is what complex conjugation on Hilbert space will correspond. That's how we got it. We started from Hilbert space with the usual complex conjugation there, and then analytically continued those things that were complex conjugate to each other to see what the relationship, and then we have to find what the relationship between these analytically continued guys is. So if we want to insert not the operator but the complex conjugate operator in the sense that is relevant to this W Hilbert space, this is the kind of operation we will have to do. Okay? Now my final claim is going to be that Gij with I replaced by the complex conjugate of the operator I in this sense is the same thing as the inner product between I and J, the usual inner product. Okay, but we have to wait till next time to see that. This will be the last formal claim I will try to make in this. Okay, next time we will use all of this to understand unitarity of arbitrary trade and languages. Okay, sorry people, I have to go. Some sort of committee.